Hello everyone, I'm Shravya and I'm from Team Victoria. So today we are going to learn NURBS curves and surfaces and followed by a hands-on session on NURBS curves and surfaces in Maya. NURBS. NURBS stands for Non-Uniform Rational Basis Splines. Now let us try to understand the meaning of each term in this definition. So non-uniform first. It means the part of the curve which are affected by individual control points are not necessary to be uniformly distributed along the curve. It means they can be non-uniform. And then rational. It means we can pull and adjust each control point on the curve. And then the basis function or basis spline. So the basis function defines how much each control point influences the curve. And the surface forms such as um, cylinders or cubic surfaces or quadratic surfaces, which are used in any computer aided design or graphics, are usually represented using these NURBS curves. So let's go in detail into the NURBS curves. NURBS curves are the mathematical representation of 3D geometry that describes a line or a circle or a curve or any surface or solid. So NURBS surfaces are used to design a very smooth and exact surfaces. Here in this image we can see a car and it is designed using NURBS curves. So NURBS curves are accurate and smooth representations, like they are not any approximations or something, they are very exact and smooth surfaces. At first, NURBS curves are only used in the design in car companies in only CAD packages, but later they were used in standard computer graphics packages as well. And these NURBS curves are used to design animals, a human face, car, and any object. So due to this, they are widely used in many industries like animation and manufacturing. So now let us see why we are using NURBS curves. It is a simple answer. It's because of their flexibility and smoothness. Because of their flexibility, we can design a large variety of shapes. And for all the shapes of NURBS curves, we have one common mathematical representation, which is a great advantage. And these NURBS curves helps to reduce the memory consumption while we're storing the shapes. Another important reason why we use NURBS is that they create invisible joints. Here in this image we can compare cars which are designed using polygon model and NURBS model. The curves in the NURBS surface are almost invisible, whereas the curves in the polygon model are completely visible and they are not as smooth as NURBS curves. So that is why we go for the NURBS curves. And one more reason why we are using NURBS curves is they are not only used in the exterior design, but they are also used in the designing the interior products, interior parts of the car. That is, we can use same type of curves in designing an engine and also external body of the car. So we can use the NURBS curves in common. So now we know what are NURBS curves and why we are using them. Now let us see how NURBS curves are used. NURBS curves are mainly controlled by two factors. their number of control points and curve degree. So the shape of the curve is going to affect when we change the number of control points and also the degree of the curve. So here in this video we can see the control points. These black dots are the control points, and here in this we can see how the degree change is affecting the curve. So now let us take a detailed look into the control points. So these control points play a major role in deciding the shape of the curve. So here we can see the control points in this image as well. And the best part is we can alter the shape of the curve at any point by just changing the control points. It is not like we design a curve and we can never change. No, we can change the shape of the curve by adjusting the control points. So when we move the control point, the shape of the curve will be changed. So, and one more important point is an individual control point doesn't show where the surface will be, but it is averaged with the surrounding points to create a curved surface. This means we cannot directly edit the surface. If we pull a control point, the surface will only move a little bit because we are averaging the change. And control points acts as magnets. The number of control points should be at least one greater than degree. If the degree is 3, then we should have at least 4 control points. So this is about the control points, and in this slide it is about the number of control points. So how can we decide how many control points we should use to design a NURBS curve? So the answer is it depends on our requirement. So when we need a very smooth surface, especially for premium products, then we have to use as few control points as possible. But when we have to design a human face or any specific shape that has many details, then we may have to use more control points to get the exact features. Here we can see in order to design a human face, we have to show every feature in details. For that, we definitely need more control points. So now about the degree. So the degree determines the influence of each control point on the curve. Here in this image, we can see curves and their degrees and control points. This is a linear curve with degree 1 and it has 2 control points, 1 and 2. This is a curve with degree 3 and it has 4 control points, 1, 2, 3, 4. As I said before, the number of control points must be one number higher than the degree. So if we have degree 3, we should have 4 control points. And it is possible to increase the degree of the NURBS curve and not change the shape, but it is not possible to reduce the degree without the changing the shape. Usually a linear curve will have degree 1, a quadratic curve will have degree 2, and a cubic curve will have degree 3. And we are done with degree now, and now knots. Knots are the list of degree plus control points minus 1 numbers. This list of numbers is called knot vector. Knot vector. It is a sequence of parameter values that determines where and how the control points affect the NURBS curves. It is represented with this equation. Now let us go to Maya and let us design a simple NURBS curve like this. So I'm opening a new scene here and I'm going to the front view. So here I'm taking a curve and I'm placing some control points to design a curve. So now I'm done with my curve. I'm pressing enter so that I can have my curve. So now we can adjust the shape of the curve by moving the control points, which is really a great feature. So we can adjust the shape of the curve by changing the mode into control vertex. And now we have our control points highlighted here. Now select the point which you would like to move or adjust, and now I'm using this move tool to move that curve. So in this way we can move the curve after drawing that, and we can also scale it, can adjust the scale this way. So now we're done with our curve. So now let us look at the hull of the curve. It is the hull which joins our control points. So this is a very simple NURBS curve, and now we'll go back to the PPT, and now we'll look at the basis function. So basis function is used in the construction of NURBS curves, and it is usually denoted by this equation. Here in this equation, C of u is the curve, Pi are the control points, control points like P0, P1, P2 in this figure, and Wi are the weights at control points, and Ni comma P of u is the basis function. Unless otherwise stated, we always assume A and B values as 0 and 1, and we assume that weight is always greater than 1 at control points. So we'll get this equation from the above values. In this equation, Ra comma P of u is the rational basis function. Pi is of the control points, we already know that, and this is a curve. So now let us see some properties of this rational basis function and then some properties of curves. And this is the representation of the rational basis function. Now let us look at the properties of this basis function. So a rational function is a rational function in U with degree p. We already know that. And the property non-negativity. What it states is, for all the values of I and p, our rational basis function is always non-negative. It means its value is always greater than or equal to 0. Partition of unity. The sum of all the non-zero basis functions on this span or in this interval is always 1. And local support. A rational basis function is non-zero on this span. All derivatives of our rational basis function exist in the interior of a knot span. When the weight is 1, then a rational basis function is nothing but a normal basis function. That is, Ri comma P of u is equal to Ni comma P of u, where C is a non-zero constant. Now, these are the properties of B-spline curves. So the first one is strong convex hull property. What it states is, if u is in the knot span, then our curve is definitely in the convex hull of the control points. We have seen the hull in Maya just before. So from that we can understand this property very easily. And then differentiability. So our curve is infinitely differentiable on the interior knot spans. And affine variance. So NURBS curves are invariant under perspective projections. Local support. Changing the position of a control point will affect only the part of the curve, because our curve is an average of all the control points. So if we change a single control point, then it is going to affect a part of the curve but not the entire curve. And next, variance diminishing property. So what it states is, no plane has more intersections with the curve than with control polygon. And the NURBS curve passes through two end control points. Those are P0 and P1. That is the first point and the last point. So we are done with the properties. Now we'll see the cubic and quadratic curves. So this one is a cubic NURBS curve. Here we have 4 control points and the degree is 3. And this is a quadratic curve which is having 4 control points. So now let us see the impact of weight on this cubic and quadratic B-spline curves and basis functions. So this is the impact of weight on cubic B-spline curves and basis function. So here in this equation, we know the control point, the weight, the curve, and the basis function. So now let us see the impact of weight on the curve at the control point P3. So if we increase the weight at control point P3, the curve is moving towards the control point. And if we decrease the weight, the curve moves away from the control point. For this curve, the weight is 3. So as the weight is more, the curve is tending towards the control point. And when we decrease the weight to 1, the curve started to move away from the control point. And when we further decrease the weight, it's further moving away from the control point. And when the weight is 0, it means like the control point 3, P3 has no effect on the curve. If we closely observe that, we can understand. Here we can see the curve from P2 moves towards P4, but it doesn't have any impact. This control point doesn't has any impact on this curve. So this is the basis function for weight 1. So here we can see that at control point P3 we have a good curve, and now let us see the basis function when weight is 1. Here for this case, this is the basis function curves, and here we can see that the curve started to diminish, and then this is the representation of basis function when weight is 0. Now let us see the impact of weight on quadratic curves and basis function. So this is a quadratic curve. So the concept is similar to the previous one. So when the weight increases, the curve is pulled towards the control point, and the weight is decreased, the curve moved away from the control point. When the weight is 0, then it has no impact on the control point. The curve has no impact on the control point. So that's how it works. And now let us see the representation of the basis function. At control point P1, the weight is applied. So when weight is 4 at control point P1, we can see a big curve here, and when weight is 3 by 10, we can see the curve started to diminish. It's a very small curve here at point P1, and when the weight is 0, we don't even have a curve. So let us look at some more examples of the same concept. And here we can see a weight is 1, and this is how the curve is, and the corresponding basis function. And when in this example here, the weight is drastically increased, that is, the weight is 10. So we can see the basis function here, it is so big, the curve is so big. So practically we don't have this much of weight. Is in a rare case we'll have this kind of weights, such big weights. And in this case the weight is very less, it's 0.1, and the curve is very small here. Let us look at another example. Here we have a NURBS curve with degree 6 and 9 control points, that is from 0 to 8, and the selected point here is P4. So when we change the weight at P4, that is when we change W4, the curve is going to affect. We are varying the W value from a very higher value 50 to as low as 0. So we can see how the curve is changing. This is a curve for W0 and this is a curve for W50. When the curve is when the weight is more, the curve is almost touching the point. Now let's take a look at the algorithm. So this algorithm is used to compute a point on the rational B-spline curve at a fixed U value. So N, P, capital U, PW, U are the input parameters for this algorithm, and C is an output parameter. So here in this algorithm we use certain functions like find, span, basis functions. Here CW is a 4-dimensional point on CW of U, and C is a 3-dimensional point on C of U, which is our output. Now here is a concept of geometrical significance of weights on a NURBS curve. Here in this figure we can see how the weight is affecting the curve. So here we have 3 curves at different weights at point P3. So we are defining the points in this way: P, N and Bi. So the N and B values can be expressed as below, where A value is this and B value is this. So finally, after these equations, we get a cross or double ratio, that is this, with 4 points. Those are P, B, N and Bi. So from this ratio, we can conclude 4 points. The first one is when weight is 0, then the curve will not have the control point will have no impact on the curve. When the weight increases, the curve pulls towards the control point, and the weight is decreased, the curve pulls away from the control point. And the final point is that when the weight is infinite, then the curve touches the control point.
So we have talked a lot about NURBS curves, and we obviously know that these are very important. Now, how do we apply the NURBS curve? To apply the NURBS curve, we need their derivatives. Derivatives tells us a lot about NURBS curve. So we try to express the derivatives of our equation Cu in terms of the derivatives of its weighted equation, that is Cwu. As you can see, we just multiply and divide the equation by its weight and we get a new expression, that is Cu equals to Au divided by its weight. Au here is our vector valued function. It represents the coordinates of the curve. Now, in order to find out the first derivative, we differentiate the equation, the previous equation, and we get this equation 4.7, which says that the first derivative is equal to a dash u subtraction w dash u of cu divided by its weight. Now, since au and wu represents the coordinates of cwu, we can obtain the first derivative. In order to compute the higher order derivatives, we have to differentiate the same equation using Leibniz rule. And using Leibniz rule, we find out that the kth derivative is given by the equation 4.8. So now that we have found out the kth derivative, we need to find out the derivatives at the endpoints of the curve, because those are very important results. So to find out the derivatives at its endpoints, we put u equals to 0 and u equals to 1. When we put u equals to 0 and a dash 0 and w dash 0, we obtain c dash 0, which is our equation 4.9. And when we put u equals to 1 and a dash 1 and w dash 1, we obtain the result c dash 1, which is our equation 4.0. Now these two results gives us the endpoints of the curve. Now we'll discuss an example. Now here, as you see on the bottom right of your screen, a figure, an arc is given. Now this arc, the knot vector for this arc is equals to 0, 0, 0, 1, 1, 1, and its weight wi equals to 1, 1, 2. Now if we find out the derivatives of this curve at its endpoints, we just need to apply equations 4.9 and 4.10, and we have the result, that is c dash 0, which will give us 0, 2, and c dash 1, which will give us minus 1, 0. So now we have a simple algorithm. We assume that our knot vector, that is u, is fixed, and the derivatives of au and wu from order 0 to d have been computed and loaded into the arrays adders and wdrs. That is, our cwu have been differentiated and its coordinate separated off into adders and wdrs. Our algorithm computes a point cu and the derivatives cku such that k lies between 1 to d. The curve point returns ck at 0 and the kth derivative is returned in ck at k. We have discussed a lot about NURBS curves and its derivatives and its uses. Now let's come on to NURBS surface. NURBS again are non-uniform rational B-splines, that is the mathematical representation of 3D geometry that can accurately describe any shape from a simple 2D line to the most complex free-form surface or solid. NURBS models are very flexible and very accurate, so we use them in industries ranging from animation to manufacturing to illustration, all of these. So why do we use NURBS? We use NURBS because they are invariant under affine as well as prospective transformations. They can easily be evaluated reasonably fast by numerically stable and accurate algorithms, which is what we're looking for. NURBS also provide the flexibility of design to a large variety of shapes, ranging from, as I mentioned, a simple 2D line to the most complex free-form surface or solid. NURBS also offer one common mathematic form for both standard analytical shapes, that is your cones, rectangles, everything, to free-form shapes. And lastly, NURBS are generalizations of non-rational B-splines and non-rational and rational Bezier curves in surfaces. So this is the most beneficial thing about NURBS. That's why we use NURBS. Yeah, so coming on to mathematical and geometrical representation of NURBS surface. Here what you see in the figure is the control net of a NURBS surface, right? So what is the mathematical representation of a NURBS surface? The mathematical representation would be the tensor product of the polynomial coefficients of two NURBS splines, right? Imagine if I'm given a curve A that has a degree k and n plus 1 control points, and a curve B with degree j and m plus 1 control points. Then my NURBS surface, the surface of those two curves would be the tensor product of A and B. And the matrix of the matrix that would be formed would be of degree maximum of j or k. And now coming on to this control net. So now what I'm doing is I'm changing the weight 1 1, weight 1 2, weight 2 1, and weight 2 2 equals to 10, and rest of the weights in this control net are set to 1. Yeah, and my vector u and v are equals to 0 comma 0 comma 0, 1/3, 2/3, 1 1 and 1. So how would the NURBS surface of this control net look like? So as you can see, the surface for the control net looks like this. It's crammed from the middle, basically because the weight in the center is more, so all of the surface tends to be crammed towards the middle. This is a very good explanation of how it reacts to weight also. And now on the left side you see the rational basis function of a NURBS curve. It's given by Rij of uv equals n in of u njm of v multiplied by its weight ij divided by summation p equals to 1 to k summation q equals to 1 to n of n pn of u nqm of v multiplied by its weight. This gives us the rational basis function of a NURBS surface. This is a very important result, and this resembles a lot to NURBS curve also. So coming on to the properties of the NURBS surface. These are mostly similar to the properties of the NURBS curves, which is non-negativity. That is, Rij of uv is always greater than or equal to 0 for all the values of I, j, u and v. Partition of unity, local support, which means Rij of uv is equal to 0 if uv is outside the rectangle given by the following tensor product. And extrema, which means if p is greater than 0 and q is greater than 0, then Rij of uv attains exactly one maximum value. Also differentiability, which means that interior to the rectangle formed by u and v naught vectors, all the partial derivatives of Rij uv exist. Also, local support and generalization are also the properties of rational B-spline functions. Now coming on to the properties of rational B-spline surface. Right, these properties include corner point interpolation, affine invariance. Affine invariance means basically an affine transformation is applied to the surface by applying it to the control points. So this is very important properties. We use this property a lot. It also has strong convexal property, a local modification property. Local modification means like if I move a point Pij or I change the weight Ij, it affects the surface shape only in the rectangle, right? In the local rectangle in which the point is placed. Also differentiability and local support. In differentiability, when we talk about the property differentiability, it means that our surface is P minus K of Q minus K times differentiable with respect to U naught of V naught. Now we'll discuss the effects of weight on our surface. As I increase the weight Ij, as I increase or decrease the weight Ij on a control point, the surface is pushed or pulled from the point Pij, depending on whether I increase the weight or decrease the weight. If I increase the weight on Pij, the surface is pulled towards it, and if I decrease the weight at Pij, the surface is pushed towards it. Basically, if I set the weight to 0, the whole control point is nullified, and that is a very important property of the NURBS surface. Here we have one more example of the change of weight. Now, as we see, the weight at 4 comma 2 initially is 2 by 3. Sorry, 2 by 5, right? So the peak is not that great. But when I increase the weight at 4 comma 2, which is now equals to 6, we can see how the peak is pulled towards the control point. This is because this is in very good property. Like we can draw an arbitrary curve and then change the weight to finally finesse it, right? And one more example, the last example which I'm going to discuss of the weight, as you can see in the point mark upwards, like if I change the weight, like I increase the weight initially at the topmost point, and the curve got pulled towards the point, right? And the and now in the bottom figure, when you see, like initially the weight, there's some weight because the curve is going towards that control point. But when I set the weight to 0, the whole control point is nullified. The line is basically a straight line between two control points, and the one control point of which I have set the weight to 0 is completely nullified. Yeah, so this is a very important property of NURBS curves. We can adjust the weight to adjust our surface and curves, right? And now we'll discuss the derivatives.
Now let us take a look at the derivatives of NURBS surfaces. Here in this equation we are multiplying and dividing S of u comma v with W of u comma v, so which resulted in this. So A of u comma v is the numerator here. So now we are applying Leibniz rule. We are differentiating the equation with respect to k and then with respect to L, which gives us the below equation. Here in this equation, in this part, both I and j are 0. Here j is 0, here I is 0, and here we have both I and j. Here what we are trying to do is we are trying to find the derivatives. So in this expression we are trying to separate this. This is the derivative. So we are trying to bring this to the left hand side, which resulted in this equation. So from this we can find the first order and second order partial derivatives of a surface. So we can calculate the points using these equations. Now here we have an example for NURBS surface derivatives. Here in this figure we can see the first and second order derivatives of a bicubic NURBS surface computed at points u equal to 3 by 4 and b equal to 1 by 4. So here we can see that the first partials are scaled down by half and the second partials are scaled down by 1/3. Now we have an algorithm. Here this algorithm is used to compute the point S of u comma v and its derivatives. Let us assume that u comma v values are fixed in S of u comma v, and the derivatives of a k comma l and w k comma l are computed and loaded into the arrays a dash and w dash. So for this algorithm, a dash, w dash and d are the input parameters and skl is an output parameter. Here in bin lj and in bin ki, the pre-computed binomial coefficients were already stored. So this algorithm gives an output skl, kl. It is the derivative of S of u comma v, k times with respect to u and l times with respect to v. So now we have some applications and design examples here. In this application, they have tried to apply NURBS curves and surfaces in a CAD system. So in this image, they created this image using the human face using 20 NURBS curves and 29 control points. So what they did is they have experimented by altering the control points and NURBS curves, and these are the images which were resulted. So in this image, they have reduced the one third of the control points. They have kept the 20 nerve skulls as it is, and they have reduced the control points. This is an image of that experiment. And here they have reduced the control points to half. So we can see that the image is not good. This is not much very similar to the human face. And here they kept the control points as it is, and but they reduced the nerve curves by one third. This is a result of the experiment, and here what they did is they kept the control points as it is, but they have reduced the nerve curves to half. So uh, here in this case, they were able to achieve a very smooth and fine face, which is much similar to the human face. So what they concluded is like this is the best approach while NURBS, designing any objects or surfaces using NURBS curves. Here we have a design example. Here in this human oral cavity has been constructed using NURBS surfaces. Here in this link they have explained in detail about how they have done this each and every process. Maybe we can you can go through this link, you will find so much of content and you will understand this is pretty straightforward. So here there is another design example. Here what they have done is they have applied the concept of reverse engineering. So what it means is like when we are trying to build a new NURBS object. So instead of starting it from scratch, if we use an existing object, then it is very easy for us to design a new one. It saves lot of time and efforts. So they have done the same thing. So uh, when they have to design a shoe, what they did is they have imported the existing shoe image and they have placed the control points uh, by taking this shoe as reference, and they have corrected the flaws in the previous shoe design in this, and they were able to achieve this with NURBS curves within 4 hours. If they have to start this from scratch, it may take 1 or 2 complete days, but as they have used this existing object as a reference, they save lot of time and cost, which is a good thing. So this is the best thing which we can do while designing a product. Here is another example. Here, nerve curves are used for the reconstruction. This is the CT scan of brain. Here they have used the nerve curves. We can see that here for the reconstruction purposes. And we have designed few objects or surfaces using nerve curves and surfaces in Maya. This is a simple glass and this is a simple vase. So now I'm going to show you some very simple object in Maya. I'm going to front view. Uh, I would like to design a flower vase. For that I am using a curve. I'm just placing the control points here in the shape of a curve. I pressed enter, and this is my curve to design a flower vase. So I'm going to the control vertex and I'm trying to edit this curve. I'm trying to adjust the shape. Yeah, adjusting the scale. So now we are good. I'm going back to the object mode. And here I'm selecting the surfaces and I'm selecting an option revolve. Apply, close. Here we have a NURBS surface. You can see that in perspective view clearly. So I'm going to that view. Here we can see a quick verse. So this is a very simple example. Maybe you can try this. And these are our references. Thank you.